Hello everyone, welcome to my second lecture in the course Limit State Design of Steel Structures. In today's lecture, we will be discussing about the chemical composition of structural steel as well as the behavior of structural steel under tensile loads. So, steel is essentially an alloy of iron and carbon, where carbon is present in small percentage and we have other elements in varying percentages as well. The alloying elements include manganese, silicon, phosphorus, sulfur, nickel, chromium, copper, etc. The percentage of iron in steel is approximately 98%. So, steel is dominated by the percentage of iron. It is mostly iron. Now, the influence of carbon on the mechanical properties of iron or steel is much larger than other alloying elements. Actually, the atomic diameter of carbon is less than the interstices, that is, the intervening spaces between iron atoms, and the carbon goes into the solid solution of iron. As carbon dissolves in the interstices, it distorts the original crystal lattice of iron. This mechanical distortion of crystal lattice interferes with the external applied strain to the crystal lattice by mechanically blocking the dislocation of crystal lattices, which as a consequence provide mechanical strength to steel. So, with increase in carbon content, the tensile strength and hardness of steel increase, but the ductility and toughness, which are otherwise very important properties of steel, they tend to decrease. Also, more carbon content will cause steel to be more brittle and will adversely affect its weldability, which is also a very important property of steel. So, if the carbon content is reduced, the steel will be softer and more ductile, but at the same time it will also be weaker in strength. So, however, by alloying chromium, nickel, molybdenum, vanadium, etc., the tensile strength of steel can be increased while retaining the desired ductility and hardness. That is, alloying chromium, nickel, molybdenum, vanadium, etc. permit tempering at higher temperatures, which actually generates better ductility at the same strength and hardness. Generally, carbon content in structural steel is in the range of 0.12% to 0.25%. When the percentage of carbon in iron is beyond 2%, we get brittle cast iron. Now, as per IS 2062-2011, that is Code of Practice for medium and high tensile structural steel, there are 9 grades of structural steel with new grade designation system based on minimum yield stress. Table 1 of IS 2062-2011 gives the chemical composition of each grade. So, as you can see, there are 9 grades running from E250 to E650, and for each grade we have sub qualities like A, BR, B0, C. These sub qualities actually indicate the requirement of impact test on the structural steel as well as mode of deoxidation. So, as per ladle analysis, the maximum percentage of different elements in steel are given in tabular form. The percentage of carbon is 0.23 for E250A grade steel, and percentage of manganese is 1.5, sulfur 0.045, phosphorus 0.045, silicon 0.40%. We have also a column for carbon equivalent value, and the maximum carbon equivalent values have been given for different grades. We have for E250A, for example, 0.42 as a carbon equivalent value. Similarly, for E250BR or B0 grade, we have carbon equivalent value as 0.41. Similarly, for E275A, the carbon equivalent value is 0.43, and E275BR and B0 we have 0.42 as a carbon equivalent value. So the sub qualities A, BR, B0 and C, they signify. For A we have impact test not required, BR, that is impact test optional if required at room temperature, that is 25 degree plus minus 2 degree Celsius. B0, that is impact test mandatory at 0 degree Celsius, and C means impact test mandatory at minus 20 degree Celsius. So we have these two terms, that is carbon equivalent and mode of deoxidation, which involves semi-killed or killed steel. So actually the carbon equivalent is the combined effect of carbon and other alloying elements on the weldability of steel. As you can see, this carbon equivalent is given by this relation, where C Mn, Cr MOV Ni and Cu are percentages of carbon, manganese, chromium, molybdenum, vanadium, nickel and copper respectively. So in case carbon equivalent is less than 0.42, steel is treated as weldable. So 0.42% of carbon equivalent is the limit for weldable steel. The steel which has carbon equivalent less than 0.2% is supposed to be weldable steel as per IS 2062-2011. Now during iron or steel making process, the hot metal contains very high levels of carbon, about 4%, and other impurities as well. So steel at this stage is very brittle and is not suitable for structural purposes. This hot material is charged to the basic oxygen furnace, where oxygen is blown into the liquid metal in a controlled manner, and the carbon content is brought down to 0.1 to 0.25%. So then lime is charged to slag off further impurities. The ferromanganese, ferrosilicon or aluminium are added to deoxidize the liquid steel. Otherwise, the oxygen present in the steel will appear as oxide inclusions in the solid state, which will be very harmful for the structure of steel. So if oxygen content is brought down to less than 30 ppm, that is 30 ppm, the steel is called fully killed steel, and if it is around 150 ppm, that is 150 parts per million, then it is called semi-killed steel. Killed steel is supposed to be better as it improves the quality of steel. Now, in order to understand the behavior of steel structures, an engineer must be familiar with the properties of steel. Stress strain diagrams furnish valuable information necessary to understand how structural steel will behave in a given situation. Indeed, satisfactory steel design methods cannot be developed unless complete information is available concerning the stress strain relationships of the material being used. Undoubtedly, the tensile test is the most fundamental type of mechanical test performed on structural steel. So, the information needed for the structural design of steel is mostly obtained from stress strain diagram of steel. So here is the stress strain relationship of mild structural steel. And the specifications for the standard tensile test specimen are also shown in the figure. So figure 1 shows the standard tensile test specimen specifications. This is the shouldered end, and this is the gauge length, which is denoted by LC. So gauge length is given by 5.65 under root of S0, where S0 is the cross sectional area of the specimen in the case of rectangular steel specimen, and LC is 5 times 5, that's 5 times diameter of the specimen in case of the specimen with a circular cross section. Now, as far as the stress strain curve is concerned, we have plotted the strain against stress for a mild structural steel specimen, and this diagram is for a typical mild structural steel specimen. So as you can see, the curve O, A, B, C, D, E, F, it represents the stress strain curve when a mild steel specimen is subjected to a gradually increasing tensile load. So various elements of the curve, that is O, A, B, represent a straight line, that is from O to A the stress proportional to strain, that is Hooke's law is applicable in this region, and point A represents the limit of proportionality, that is the stress beyond which linear variation of stress and strain ceases to exist. Point B represents the elastic limit, that is the maximum stress up to which a specimen regains its original length on removal of the applied load. Then we have C dash and C, which denote the upper yield point and the lower yield point. The upper yield point C dash is observed if the load is applied rapidly, whereas the lower yield point C is observed if the rate of loading is slow. So in many of the structural steel hot rolled sections, the upper yield point C dash is not obtained due to residual stresses from the hot rolling process of the steel sections. Hence, it has no practical importance. And point C represents the yield point at which there is a definite increase in strain without any further increase in stress. The stress corresponding to the lower yield point C is thus the yield stress denoted by Fy. And for the region OC, this region, the material is elastic, and the slope of the stress strain diagram in this portion is called the Young's modulus or modulus of elasticity, and that is given by E is equal to 2 into 10 raised to power 5 Newton per millimeter square, and it is same for all grades of steel irrespective of the grade. So the strain that occurs before the yield point is called elastic strain. Now CD represents the plastic yielding, or it's called a yield plateau. It is a strain which occurs after the yield point with no increase in stress. So there is constant strain with no increase in stress. So the strain which occurs after the yield point with no increase in stress is called plastic strain. So this region denotes the plastic strain. So DE represents the strain hardening range. It is a range where additional stress is needed to produce additional strain. Strain increases rapidly with stress till ultimate load is reached. The increase in stress and strain in this strain hardening range is probably due to the rearrangement of crystal structure of the steel. The point E represents the ultimate stress, that is the stress corresponding to ultimate load. The initial slope of this region is about 4% of the modulus of elasticity. At a certain strain of 0.2, the stress reaches its maximum value, which is called the ultimate strength of steel, that is this point. And this ultimate strength of steel is denoted by Fu. So ultimate tensile strength, or the minimum ultimate tensile strength, is given by the ratio of the ultimate tensile load, there is the maximum load, divided by the original cross-sectional area of the specimen. Now after reaching the ultimate tensile stress, a localized reduction of cross-section takes place, which is called necking. So beyond this point there is a localized reduction in cross-section, and this is called necking. Stress follows with a rapid increase in strain till the specimen breaks at point F. So point F denotes the breaking stress, that is the stress corresponding to breaking load. Now after we have performed the structural tensile test on steel, if the fractured surfaces of the two pieces of the steel specimen are found to form a cup and cone arrangement, then it indicates ductile fracture. In summary, the largest stress for which Hooke's law applies, or the highest point on the linear portion of stress strain diagram, is called the proportional limit, and the largest stress that a material can withstand without being permanently deformed is called the elastic point, rather elastic limit. And the stress at which there is a significant increase in elongation or strain without a corresponding increase in stress is said to be the yield stress. So point C denotes the yield stress. It is the first point on the stress strain diagram where a tangent to the curve is actually horizontal. So if you draw a tangent to this point, it will be horizontal to the original line. The yield stress is probably the most important property of steel for the designer, as the design procedures are based actually on this value only. So beyond this yield stress, there is a range in which a considerable increase in strain occurs without increase in stress. The strain that occurs before the yield stress is referred to as elastic strain, and the strain that occurs after the yield stress, rather after the yield point with no increase in stress, is referred to as plastic strain. Plastic strains are usually from 10 to 15 times as large as the elastic strains. Now, basically, yielding of steel without stress increase may be thought to be a severe disadvantage of steel, but in actuality, it is a very useful characteristic of steel. It has often performed the wonderful service of preventing failure due to omissions or mistakes on the part of designer. When the stress at one point in a ductile steel structure reaches to the yield point, that part of the structure actually will yield locally without stress increase, thus preventing premature failure. This property allows the stresses in steel structure to be redistributed. So it might also be said that a steel structure has a reserve of plastic strain that enables it to resist overloads and sudden shocks. If steel didn't have this ability, it might suddenly fracture like glass or any other brittle material. So this is a very important property of steel, and this property is called ductility. That is, it undergoes large inelastic deformation without fracture, or we may say large inelastic deformation before fracture. Now we have the tensile, high tensile steel, and for high tensile steel the stress strain relationship is as shown in figure. For high tensile steel there is no apparent yield point because there is a continuous curvature in the stress strain diagram. So in order to calculate the yield stress for such type of steel, we generally draw a line parallel to elastic portion or proportionality limit, and this strain is generally an offset strain of 0.2%. that is, at an offset at a strain of 0.2%, we draw a line parallel to elastic portion of the stress strain diagram, and the point where it meets the stress strain diagram, that marks the yield stress for that type of a tensile steel. So that is all for today. Thank you.